Have you ever noticed these warnings in your model and wondered what might be the problem or how to rectify this? Well, you are not alone. This is a very common issue with any structural model, and in some specific case, this might be fatal for structural stability. Do you know how to identify and rectify these instability problems? Hi, my name is Surajit Ghosh, and in this video, I will discuss about different reasons of instability and rectification techniques using multiple real project models. I have already covered the basics of zero stiffness and instability condition in the first two parts, including the impact on the structure and how member truss and release specification generates instability condition. Also, in the last video, I have discussed how we can gradually change the percentage of release to decrease the deflection and stabilize the model. To sum up, we should follow these steps to eliminate the instability problem from any model. When an instability or zero stiffness problem is reported in the output, first review the analysis results, check the statics check result and deflection value, check the load case for which it is reported, review the results to find out whether this problem has any significant effect on the structural behavior or not. If this is a non-issue, then simply ignore the warning. But if the model is affected or unstable due to the instability or zero stiffness condition, then rectify the model and eliminate the issue by changing the stiffness value. Change the release command or truss specification to partial moment release command. Change the support condition. Check for any connectivity issue. After modification, reanalyze and once again review the results. If the deflection value or time period is still over the allowable limit, then continue the process till the model is stable. Let's apply this theory on few real-life models. First one is a structural model of a bus stop. This type of bus stop or car parking structure is very common. Tube sections are used as a column and the roof is supported entirely on these two columns. Three loads are applied on the structure: self-weight of the members, inclined floor load on the roof to replicate the load coming from the roofing seat, and wind load from the lateral direction. After analysis, several warning and notes are reported in the output file. There is a warning that the structure is disjointed, and rest of the warnings are related to instability. At node 6 and in all translational and rotational direction. This means there is no stiffness at any direction at this node. So program includes few weak springs during analysis, which we have already discussed in the second part. What is the reason of this instability and can we ignore these warnings? As per our theory, we need to check the deflection value and statics check result to confirm this. From the post-processing mode, we can check the deflection of this structure. Huge deflection is reported for all the load case in all directions for node 5 to 14. That means the entire roof of the structure is not stable. There is also a large difference between applied load and reaction, which we can confirm from the static check results. This means these warnings are not harmless and we need to rectify the model. There is no truss or moment release used in this model. The reason is something else. Remember, a warning is reported that the structure is disjointed. From the utilities, structure tools, we can check this condition. using multiple structures option. See, there are three different structures present in this model. The columns are separate and roof is not connected with these columns. This is a modeling error as there must be a connection at node 2 and 3 between the roof and the column. But as these members are not divided at node 2 and 3, so there is no connection between the roof and the column. And when the load is applied on the roof from any direction, there is no stiffness or restriction to resist the load, which results a huge deflection and structurally unstable condition. To solve this problem, we need to break these members at node 2 and 3 to establish proper connection. We can select all the members and then from beam tools, intersect the members. Now these members are connected with the column and we can reconfirm from the structure tools that there is no disjointed structure. Analyze the model. This time, no instability warning is reported. The structure is now stable. Deflection value is within allowable limit. We can further reduce it by increasing the section size. Static check results are also okay. For this model, modeling error or incorrectly connected members are the reason of the instability. Similarly, presence of orphan node, zero length member, or improperly connected beam and plate can cause this type of instability problem. Next model is a mat foundation structure, like a pump house or base slab of a high-rise building. Plate mat support is assigned with compression-only spring, and the direction of the spring support is at the Y-only direction. For this model, I have removed all other loads, and there is only a gravity load, self weight of the structure, a lateral load from X direction, like wind or seismic load, and a combination load case with these two loads. In the output file, 26 warnings are reported, most of which are instability warning in X and Z direction at joint 372. First, check the static check results. Load case 1, it seems okay. For load case 2, there is a huge difference between applied load and reaction. Same for load case 3. Also, deflection in X, Y and Z direction and rotation about Y and Z direction is very large. This structure is not stable. What is the reason? Check the support condition. We have assigned a plate mat support and soil spring is specified in the Y only direction. This means a spring support is assigned in the Y direction only. The spring constant value is same as the subgrade modulus. All other directions are free to move or rotate as there is no support. Consider a roller support which can move or rotate in all directions except vertical direction. This Y-only mat foundation is similar to a roller support condition. Only replace the fixity in Y direction with a spring. So it has only one restricted direction in translational Y, and when a lateral load is applied, the whole structure moves and rotates in the load direction. This is not the actual scenario of any mat foundation. There must be soil or other type of support to resist the horizontal and rotational movement. So we need to change the support direction from Y only to Y. Y means soil spring in vertical direction and other three directions are restricted or fixed. We can also assign 50% of the soil spring value in other two directions. Analyze the model. Now there is no instability warning. Check the statics check result. Load 1 and 3 seems okay. There is no difference. But still there is a mismatch for load case 2. We need to check the reason for this. Load 2 is a purely lateral load. A load from x direction is applied on the structure. And that's it. Weight of the structure is also not considered. When program analyze for this load case, a weightless structure with no gravity load is considered, which is subjected to some lateral load. So there must be some lateral movement. But this is not the real case. It is not possible to apply a load without considering the weight of the structure. That's why this isolated lateral load has no significance on the analysis. We need to consider this load case only when it is combined with the gravity load. For example, check load case 3. Here, the lateral load is combined with the self weight, and for this load case, statics checks results are okay. That means this structure is now stable. We need to review the model on basis of the load case and disregard results for those loads which are not realistic. To solve this problem, we can replace the primary load case with a reference load. This is the same mat foundation model. Only difference is I have created two reference load case to define the primary loads. Gravity and lateral loads are defined under this reference load case, and then these loads are combined using a repeat load case. As you know, STAAD does not analyze the loads defined under a reference load case. It is only used as a reference for combination purpose. This not only reduces the analysis time, but also eliminates the results for unrealistic isolated primary loads. Check the statics check results. It is reported only for load case 3, and the applied load and reaction value match. You can define primary loads under reference load case to eliminate any confusion related to the results reported for primary loads. Next is a frame model like a concrete building. I want to check the fundamental time period of this structure. Under load case 1, mass model is specified in 3 directions and modal calculation requested command is included. This command performs eigensolution and reports the time period of first 6 modes, from where we can get the fundamental time period of the structure. We can further use this time period for static seismic analysis by specifying the px and pz parameter. You know about this, right? Let me know in the comments if you want to know more about static seismic analysis using more accurate time period. In the output file, an instability message is reported in rotational y direction. Also, there is another warning related to eigenvalue. A rigid body mode is detected and probable reason is mentioned as modeling error or lack of support. Check the time period. For fast mode, it is almost 13 days. That means if the structure is displaced due to lateral load, it will take 13 days to complete the cycle and return to its initial position. It's huge and not normal. Check the displacement diagram. Whole structure is out of screen. Displacement in x direction and rotation about z-axis is huge. The structure is unstable and must be rectified. The reason is we have assigned pin supports which has no rotational stiffness. If a lateral load is applied on the structure, it will rotate infinitely. That's why there is a huge displacement and time period is reported as several days. To fix this problem, we need to assign rotational stiffness at the support level, change the support from pinned to fixed, which has full rotational restraint, and analyze. Now there is no instability. Time period is also okay. This is another case where instability causes severe problem and must be rectified. If you perform static or dynamic analysis with an unstable model, all respective results will be incorrect. Next model is still building. For this model, I want to perform stability analysis according to Eurocode or IS 800 code. Dead load and live loads are applied on this structure. Along with that, two repeat load cases are created where dead and live loads are combined and notional loads are applied in the x direction and in z direction. A second order P delta analysis is performed to consider the second order effects during analysis and member design. There is no warning reported for this model, only one note. In the statics check results, we can notice for all load case, there is a difference between applied moment and reaction values. Does this mean this structure is unstable? To understand this, we need to go through the basic of second order analysis. I am not going to cover this as it requires more time. Just an outline. For an iterative P-delta analysis, the displaced shape of the structure is considered during analysis and additional moment values are calculated which generates due to the eccentricity of the displaced shape from the original location. This moment is not an applied moment, rather it is generated during analysis, and that's why the reaction moments are greater than the applied force and there is a mismatch in the statics check results. This is very normal for any second order analysis. Do you know for a second order analysis how to confirm whether the structure is stable or not? For that, we need to perform a linear static analysis and review the analysis results. From the input editor, after cellpoint command, we can add perform analysis and finish command. This will perform first order analysis considering the cellpoint only, analyze, and check the statics check results. The difference is now 0, which suggests that the structure is stable. I always recommend to perform a first order analysis with the final model using cellpoint before any second order analysis. This will confirm the structural stability and clears any confusion. That's it. There are several other reasons of instability condition, like when we release a mix at both ends of the member. Member can rotate freely about its own axis, which generates instability condition. Or when we use ignored plate stiffness. I will try to cover these conditions later. Feel free to comment if you need any clarification. Thanks for watching.